Hi everyone, my name is Prakash NC, M.Tech in Computer Science and Engineering from PESIT. Today I am going to give seminar on verification by model checking. The agenda or outline of my topic is motivation for verification. Second is linear time temporal logic. Linear time temporal logic consists of subtopics: syntax of linear time temporal logic, semantics of linear time temporal logic, practical pattern of specifications, equivalence between linear time temporal logic formula, adequate sets of connectives for linear time temporal logic. Let us see what is motivation for verification. Verification. Verifying the correctness of computer system. Computer system is nothing but hardware, software, or combination of both hardware and software. Why we need this? Because verification is motivated by safety critical systems, commercially critical and mission critical. Safety, everyone nowadays, everyone needs the safety of their systems, because they might store some important data that should not be shared with others. And commercially critical, mission critical. Mission, to achieve some goals or to do some important work, some group of companies or group of people working together, and they should not want to share their information with others. So that critical must be under safety and should be need to verify in levels to check whether the system is working properly or not, according to their guidance, according to their will. Verification parts. Formal verification technique consists of 3 parts. What is this formal specification technique? Nowadays, every industries or every organization or any other IT field looking for formal verification to record their works, to record their project, to record their what are the things going inside that organization or any fields inside them, to maintain well-versed records. So nowadays all the organizations are adapted formal verification technique. Formal verification technique consists of 3 fields: framework for model systems. Model system, that describes the specific language, and specification language for describing the properties to be verified. Specification language helps to describe the properties to be verified, which are the properties to be verified in that project or in that organization, within that organization or within that industries, IT field, etc. Verification method. This method for establishing if the description of a system satisfies the application. If the overall description what you have given description is satisfied, we need verification method whether it is satisfying our given description and system or what. To take care of that, we need specification verification method. Classification. Approaches to verification can be classified in several ways, because in every field follows some different kind of verification based on their work, based on their project, based on their system's needs. So according to their requirement, classification of verification can be classified as proof based versus model based, degree of automation, full versus property verification, intended domain of application, pre versus post development. First, let us see what is proof based verification. The system description is a set of formula tau in a suitable logic. Earlier I told that we need 3 parts in the formal verification method. In that, first one is system description, second one is specific language, and third one is verification method. Here the first system description is set of formula in suitable logic. Specification is another formula tau. Verification method we are following is finding a proof that tau deduce that pi. It typically needs the user guidance and expertise. To do any kind of verification, the person who will work with that knowledge and who got some expertise in that domain has to be conduct that verification in order to say whether the system is working properly or not. To do that, we need user guidance, and as well as you must possess some expertise in that domain. Model based verification. System is represented by a model. We are taking M. We represent model as M here for an appropriate logic. The specification is again represented by a formula. The verification method consists of computing whether a model M satisfies pi. Verification overall method. What is this model based? First of all, we took system is represented by model, and we choose an language by choosing formula pi. And the third one is verification method consists to compute whether that model satisfies that pi formula. Computation is usually automatic for finite models. For finite model, in the sense, if we go for verification, the model should terminate in some state. So it consists of only finite models, and that should be automatic. Which one, after verifying which one, we select which the next one for verification. Degree of automation from fully automated to fully manual. We check whether that system what we have verified automatically, whether that working fine with whether we conducted manually. Next one is full versus property verification. The specification may describe a single property of the system. The overall specification what we given that describe only single property of the system, or it may describe its full behavior. If you want to describe its full behavior, that will be expensive, which includes to record each and every steps and what are the system needs and all. So it going to be an expensive. The next one is intended domain of application. The domain in model checking, we are mainly focus on hardware and software. Whether to go in sequential manner or whether it is in concurrent. While verifying whether it is reactive or going to be terminate. Reactive to its environment. When you feed an input to that model or the system under verification, we must give an reaction. Whether it must, if it is an interactive model, we feed an input and we expect some desired output from the model, whether it is working fine or not. We will decide based on that what output it produces by taking the input. And it is not meant to terminate. Operating system, examples, embedded systems, computer hardware. The next one verification model is pre versus post development. Verification is of greater advantage if introduced early in system development. Of course, if we introduce the verification in before the system development, we can figure out what are the mistakes we have done and can we correct, or should we bring one more logic or one more method to solve this problem if something arises in that while we recording before going for development. So the best case in overall these things, pre versus post development, we need to check whether the system is what we are described overall for the system, whether it is intended with our desire or not. Next one is model checking. What is model checking? Model checking is an automatic model approach. It is intended to be used for concurrent and reactive system. This model checking is purely towards concurrent and reactive systems. What is the main purpose of this model checking? The purpose of reactive system is not necessary to obtain a final result, but to maintain some interaction with its environment. In concurrency, we have some bugs that are not non-reducible and they are not covered by test cases. We have so many test cases for while we going for verifying a system, but I don't say that the test cases we have undertook is not at all going to cover all the things in that working environment. To verify that a system satisfies a property, we must do three things. First, in model checking, the model are transition systems. The property pi are formulas in temporal logic. Property, every property should be converted as formula in temporal logic. Next step, model checking steps. Model the system using the description language of model checker. As I said, we going to represent model as M. Code the property using the specification language of the model checker pi. Convert the property what you are recorded into formula in specification language. Let us say it is pi. Run the model checker with its input to feed the model M and pi. It is formula which we converted property as formula. So overall model checker looks like this. We have feed the input by taking the property as formula, and model checker decide whether that information given by the input and is going to produce the output, and later that developer decide that whether that what the output he got, whether it is appropriate or not. Based on that, you are going to record that error trace, what are the error and what should be the output for this input. You're going to record all those things. In the next step, you're going to review that what is the earlier output while giving the input to that model checker. Later on that, you're going to develop from the crash saying that this is the output for this input. You're going to record all those things, and if you found some error, you're going to record in record log. Linear versus branching. Linear time logic, think of a time as a set of paths. Linear time, one after the other. Linear time, every seconds in terms of units or minute, that should be the path, entire path will be set of paths should be in time logic. Path is a sequence of time instances either in seconds, either in minutes, with that should be decided by the developer or the person who verifying the system. Branching time logic represent time as a tree. Branching, as you will know, tree has many branching. With that, we are going to represent that time as a logic and in terms of tree in branching time. It is rooted at the present moment. If you are going to check on some time logic, the first instance itself is rooted and the later parts are going to branch out in the future. Many logics were suggested during last year that fit into one of the above category. So many people intended to this domain suggested some category of the above, whether to go for linear time logic for some kind of verification and branching time logic for some kind of verification methods. We study linear time temporal logic in linear time logics and computation time logic in branching time logics. What is the difference between linear versus branching? As you are seeing, linear time, every moment has a unique successor. If the one thing repeats here, that should not be repeated next time. That is unique successor. In branching, in every moment several successors. There might be a several successor in every moment. In linear time, infinite sequences. it might be words. Infinite sequences means that we can compress it into words. In branching, infinite tree. In linear time temporal logic is LTL, and in branching we represent it in CTL. We can see in that figure, every time, as I said, every time there must be unique in linear, and there might be a several successor in every moment. The idea is that a formula is not statically true or false in a model. We base that the formula we are checking is not, we not decided yet that whether it is true or false within that model. If that formula is true in that some model, and it might not be true in that in other model. So we have seen so many model checking some properties there. If we take some formula and we feed something in that any one of the model checker algorithm or method, that formula may be true in some model or should not be, and it be false in some models. The model of temporal logic contains several states. A formula can be true in some, as I said, a formula can be true in some and false in others. The static notion of truth is replaced by domain 1, which is saying the formula may change the truth value as the system evolves from state to state. When system takes state from first state to next state, the formula may change their truth value, whether the formula may true in the one state may not be true in the next state, and that will be may not be false in the next state. That's it. That's how this property is saying. The logic we are using that while checking might be linear time temporal logic or computation time logic. Linear time temporal logic, it is temporal logic with connective that allows us to use the future. We can use it. Temporal life provides us as connective, we can use that in future. It models time as a sequence of state extending infinite into future. We can use it in future also as a sequence of states. We can extend this LTL, linear time. This sequence of states, sometimes called computation path or simply path. The sequence of paths LTL produced can be seen as computation path, or we can see it is simply a path. Syntax of linear time temporal logic. The formula can be produced using like top, bottom, p variable, not formula, using and connective. And connecting use two variable, or connective also two variable, and implies also use two variable like next state, some future state, global, universal, weak until, release. Some formula use two variable, and like not formula use only one variable. The syntax, where P is any proportional atom, P, it might be any proportional atom from some set of atoms. X, F, G, U or W are temporal connectives, as I said in while defining syntax of LTL. Temporal connectives. As I said earlier, linear time defines some temporal logic. These are all those temporal logics. X meant for next state, F some future state, eventually, overall it is eventually. G all future state, U meant for until or release, weak until that is defined with W. So we have seen so many connectives. Let us see the precedence of those operators. First, unary operator including negation have strongest precedence. If we come across the formula negation of P universal Q is passed as first negation of P, then it includes the result of negation of P universal and Q rather than negation of P or Q. Temporal binary operator have stronger precedence than non-temporal binary operators. If we come across P and Q universal R, first it going to parse Q universal R, later it going to parse with P and the result of Q universal R. The precedence over propositional logic is usual. First going to do the AND operation, then the OR and XOR, finally implies and equivalence. Let us see one example. Are we going to parse with the temporal logics? F with some proportional atom ANDed with global proportional atom Q implies P weak until R. According to the precedence rule, the system going to parse the above formula like this. As you seeing this, first going to parse implies, later and weak until. These are all the temporal logics. F, G, P, F in P as proportional logic to F, which is future or it is eventually, and Q is global, and P weak until R, as you seeing that in the picture. Semantics of linear time temporal logic. Transition systems. A transition system is a structure where S is a set of states leads to the sum L, labeling function, where S is a set of state, as I told you, and implies is a binary relation on S such that every state that is there belongs to S as some S dash belongs to S, even that the next state also belongs to S, that overall state. L is a labeling function. When we state with an when we take a state from that global state, it is going to lead with the next state that might be an proportional atom. P of atom means the power of set of atoms. How many atoms involved in that set of formula? The interpretation of the labeling function is that each state S as a set of atomic proposition, that is L of S, which are true at that particular state. We'll see one example. S consists of S0, S1 and S2. As you seeing, S0 consists of PQ as proportional atom and S1 as Q, S2, Q and R. These are the proportional atom for the state S0, S1 and S2. And S0 is transitioning from S0 to S2 and S0 from S1, S0, S2 again to S0. So there is a transition S0 to S1 and S1 to S1 itself, S2 to S1, S2 to S0, S0 to S2. So proportional atoms of S0 is P and Q. Proportional atom of S1 is Q. Proportional atom of S2 is QR. Deadlock. We will call the transition system simply models in our discussion. What do you mean by really deadlock? According to the definition of model, for each state, yes, there might be at least one state in the next. If you are in the one state, and we might be saying that we have one more state in the next, and no state in the system may be in deadlock. If a system has a deadlock, we always add an extra state SD representing the deadlock. Deadlock can be represented like this, and here we saw that deadlock from S3 or deadlock. S3 does not have any further transition, so the system is deadlock. We can add one more state SD. SD as a state to show that the system is in deadlock. Some practical patterns. It is but ready does not hold. G globally, as you seeing, started and not started. Overall is not started globally. For every state, if a request occurs, then it will eventually be acknowledged. If we requested one state, that should be produce an acknowledgement, and the system enabled for eventually enabled, and it will be eventually be permanently deadlock, and eventually and globally a deadlock. Some practical pattern. A certain process is enabled infinitely often on every computation path, globally and eventually enabled, and that might be enabled in overall, and even it will be false, and further it is enabled in future. If a process is enabled infinitely often, then it runs infinitely often. If it is enabled and in continuity enabled in the next also. Equivalence. We say that two linear time temporal logic formulas pi and r cement model sequentially equivalent if and only if those two are pi and psi are equivalents and can be interchangeable. And we have duals, future and globally. As you said, not of G, some atomic proportional atom P can be dual, can be written as in future not of pi, and in future not of pi is global not pi, and X is next state is dual with itself. Equivalence, future distributed over R and G over and F, pi and psi. We can see all those things in the formula. These are all the duals, but these equivalents do not hold. Equivalence, we can express F and G by universal and release functions. So you are seeing this one, and we can release work rather similarly like universal and release. Adequate sets. What is adequate sets? A set of connective is adequate if all connective can be expressed using it. X cannot be derived from any combination of others. Each of these sets is adequate for LTL. The sets consists of, which is unique adequate to LTL, consists of universal and next state, release and next state, and weak until and next state. Thank you.